So now you see what I am doing here is basically I am trying to find an estimate of the mass and radius of a star at the verge of gravitational collapse. But why are we talking about gravitational collapse? Just now you saw that for neutron stars the gravitational effects are very much important compared to that for normal stars and white dwarf. Now I am going to exploit this thing. So you see this Schwarzschild metric which we write down here previously, it basically becomes singular at this point. When the bracketed term becomes equal to, it blows away, and this happens at this particular point. And this is basically, I can write it down in G is equal to C is equal to 1 units as R is equal to the Schwarzschild radius. So this is the Schwarzschild radius. So basically this entire metric becomes singular at this Schwarzschild radius, right? Now, so what happens for normal stars? You see, for normal stars, we have this Schwarzschild radius much deep inside the normal star. So, if this is the gravitational radius of the star, then the Schwarzschild radius is much inside, very much inside. This is for normal star. Same for white dwarf. Same thing. But what about neutron star? The fact that the general relativistic effects are slowly becoming more and more important, this can be seen as this thing here. In this case, for neutron star, this Schwarzschild radius is not at all that much deep inside. It is inside, but not that much deep inside the neutron star. And what about black hole? Oh, what is a black hole? Basically, black hole is a object, stellar object, where your Schwarzschild radius is more than or equal to your gravitational radius. It doesn't have a surface. It will eat away everything. হচ্ছে বড় হ্যাংলা সম্ভবই না সব খেয়ে নেবে হ্যাঁ So this is a very basic idea. So I am just trying to play with the Schwarzschild radius, and basically I am trying to play with the gravitational collapse. ঠিক আছে, এবারে দেখো আমি কি করব। Now I am going to exploit this fact that for normal star it is much inside, neutron star it is not very much deep inside. For black hole the gravitational radius is basically on or inside the Schwarzschild radius. Now if I utilize this concept, then it is possible to estimate the mass and the radius of a star near the limit of the gravitational collapse, having this Schwarzschild, this particular condition, R is equal to 2m, and this will give me basically the estimate for the maximum mass of neutron star. This is one of the ways of estimating the maximum mass of a neutron star, right? Now there is another way also. You remember the Chandrasekhar mass limit we talked about, how we approach the problem, how we approach to finding the maximum mass of a white dwarf star, or basically where we have the basically relativistic degenerate electrons more and more, right? Similarly, the same thing can be done here for relativistic degenerate neutrons, and similarly, following the prescription of this Chandrasekhar mass derivation, we can have yet another estimate for the maximum mass of neutron star. Well, that is another procedure, but this one is a little bit different. Now let's see what it gives us. So let us assume that gravity packs the nucleons. Now gravity will pack it, fine. But up to what level? We do know that I am existing here, you are existing there, we are talking to each other. This is the great manifestation of the repulsive core, which exists at around 0.5 Fermi. Had there been no repulsive core, what will happen? Everything will just collapse. বুঝতে পারছো? সব কিছু এক হয়ে যাবে। আর কোনো স্ট্রাকচারই থাকবে না, কোনো ভ্যারাইটিই থাকবে না, আইসক্রিমও থাকবে না, পিৎজাও থাকবে না। The very existence of ice cream and pizza is basically due to the repulsive core. You can say, বুঝতে পারছো তো? Because of this there are so many different chemical species, so many different chemical reactions, nuclear species, chemical species and all that. Now gravity is playing with that. This is what we'll do. Ultimately there will come a point when gravity will even collapse it beyond this repulsive core and everything will keep on collapsing and we will reach a singularity. Why singularity? Because we do not know all the laws of physics, they don't matter anymore. Everything is becoming a point. It is very absurd, but this is what I think happens. So the thing is like that. Okay, I will talk about it later on. So let's see what happens until not beyond the collapse, beyond the repulsive core, but up to the repulsive core. So let's see here. So let's assume that the gravity packs the nucleus up to the repulsive core, right? Which is 0.5 Fermi. So we estimate that here আমরা এবার এই যে r is of the order of r0 e to the power 1/3. ওই এস্টিমেটটা যদি আমি নিই, then you see, and I put r is equal to twice of m. If I put these things together, then you see this is what I am getting. A of the order of, you remember this thing, this number, A of the order of 10 to the power 57, R of the order of 7 kilometer and mass of the order of 3.5 kilometers. Okay. Okay. Now you see the matter at the edge of the star. We have been talking about the collapse, how to find the limits of mass and radius of a star at the verge of gravitational collapse. Now you see, let us consider matter at the near the edge of the star. Now what will happen is that near the edge of the star, you see, it is less compact than the center. Obviously, density grows towards the center. Okay, and as a result, what will happen? We will expect larger radius and smaller mass. So let us assume this part. So let us assume that the mass is around twice solar mass, and the radius is approximately your 10 kilometer. আগে কত ছিল? দেখো আগের এস্টিমেটটা যেটা বার করেছি 7 কিলোমিটার, right? So I am assuming a little bit larger radius and mass little bit more, and this will give me average density of 10 to the power 15 gram per centimeter cube. Fine. Now let us compare this with the density of the normal symmetric nuclear matter. N is equal to Z case. You can find it a large number of ways. Density. Okay, basically mass by volume. Mass you know and volume you can estimate, right? And you will find that average estimate is around 2.5 into 10 to the power 4 gram per centimeter. But now something very weird happens. Why? Look at the numbers. Just look at this and this. So this means that compared to the density of a normal symmetric nuclear matter, the density, average density of a compact star near a gravitational collapse is how much? 4 times more. Have you ever heard about such a thing? Have you ever heard about in your entire course of study anywhere? কখনো কি দেখেছো? The density you are encountering now, stable density. It's not just keep on going on. I am talking about neutron star, which is in hydrostatic equilibrium, right? So it's a stable star, compact object, neutron star. So basically we are talking about star having super nuclear densities, more than your average nuclear density, right? Now let us estimate this. Estimate the gravitational energy of a uniform density neutron star. Now this is very, you know this expression, of the order of 3.5 m square by r. You can do this and you will get this value. Again I am talking about G is equal to C is equal to 1 units. So it comes out to be around 0.54 kilometer. And in terms of energy it is 4 into 10 to the power 15 MeV. Now I am giving you two homeworks. You have to think and you have to tell me in the next class what is the consequence or what can you infer from these two observations. Observation number 1. Compare this gravitational energy of a uniform density neutron star with the total gravitational mass. What is the total gravitational mass? We have started talking about this two solar mass star. So just take a ratio. You see the entire gravitational energy is 80%, huge number. First observation. Next observation. Note. Remember in the just previously I was talking about the baryon number. What is the number of nucleons or number of particles inside a star near the gravitational collapse? The number was around 10 to the power 57 order. So 10 to the power 57 nucleons and this is the total energy available. So what is the energy per nucleon? Around 157. Again it's a huge number, 20 times more than your normal matter, 8 MeV per nucleon. So what is the consequence or what can you infer from this? Think about it and tell me in the next class. Okay? Any more questions? আজকে এই অবধি থাক তাহলে। Okay, so you see in the class today we did a lot of calculations and I found that in one of the calculations there was some error. So let me first redo that part. So this part is regarding the calculation of the baryon number and the size of the neutron star, right? So basically you see in this part where we were writing like this, r is equal to twice m, and then let me put it in this condition. So m is equal to a into m, and then on this part side I will just put in the value of the r equal to a0 a to the power 1/3, and so this will give me twice am. So this gives me basically a to the power 2/3 is equal to r0 divided by twice m. Okay, and the value is around, this value is around say 2 into 10 to the power 38, and later on this gives me basically a approximately 2.6 into 10 to the power 57. Okay, so this is the correction, this calculation. So do note this. Okay, so the next calculation is regarding the mass density or mass density of normal nuclear, say normal nucleus. Okay, fine. So let me first write down the number density of nucleus, and you know this very well. So number density n is equal to mass by 4/3 pi r cube, right? Now this we can write it as a by 4/3 pi, and this r I can write as a constant which is 1.25 Fermi meter into a to the power 1/3 whole to the power 3, right? So this, and if we work it out you will see the value comes out to be 1.22 into 10 to the power 44 per meter cube. Now experimentally it has been found that this value of n comes out to be around 1.6 approximately. This is the number, around 1.6 into 10 to the power 44 per meter cube. So we will use this number right now. So this was basically the number density of the nucleon. Now what about the mass density? Well, the mass density is equal to the number density into nucleon mass, right? And so this is equal to just 1.6 into 10 to the power 44 per meter cube into 1.67 into 10 to the power minus 27 kg, right? And you will see that this comes out to be approximately 2.6 into 10 to the power 14 gram per centimeter cube, and still this number, and so this is the number you get. Okay, so now remember, in the class today we talked about two very important things. One is this, you see, the gravitational energy, right? The gravitational energy divided by the total gravitational mass divided by total grav mass, and we found that this number is approximately 18%. This was the first observation, right? And then the second observation was that, you remember this, right? When we were calculating this Eg, we found the Eg to be around 4 into 10 to the power 59 MeV. But remember that the total number of baryons is around 2 into 10 to the power 57, right? And this gives me, so just from these two things I get an idea that the gravitational energy per nucleon, E by A, in the neutron star, this is of the order of 157 MeV per nucleon. Now if we compare this with the E by A for a finite nucleus, what do we found? The finite nucleus has just 8 MeV per nucleon. So this means that compared to this, the neutron star is around 20 times more bound. Okay, look at the values over here. Now one thing before I continue, it is very important to remember that the classical estimate of the gravitational energy is not the binding energy of the star. Why? Because it does not take into account of the compression energy resisting the assembly of nucleons in a star arising from the Fermi pressure and the short-range repulsive nuclear force. Nonetheless, it is important to see that the gravitational binding energy per nucleon in a limiting mass star is of the order of 100 MeV per nucleon. So this means that the weakest force is binding the nucleons in a neutron star, and this is much more strongly, the binding is much more strongly, you see, 20 times more strongly compared to a finite nucleus, that is compared to what the strong force binds them. So what is happening? The answer to this dilemma lies in the range. You see, the nuclear force acts only on its nearest neighbors, right, that lie within its range. Typically, the several next nearest neighbors, but each particle in a star feels the gravitational force of all other particles. Okay, so what's the moral of the story? The moral of the story is basically neutron stars are bound by gravity and not by the nuclear force. This is important. This is the moral of the story. Okay. So basically, we had two very important observations. The first one is that the gravitational energy is a significant fraction of the total gravitational mass of the star, which is a significant fraction. And the second observation is this one. When we compare the binding energy per nucleon, the gravitational energy per nucleon for a limiting neutron star with that of a finite nucleus, and then considering the long range, infinite range of gravity compared to the very short range of the strong interaction, we get this idea, we come to this conclusion that in fact indeed it is the gravity and not the nuclear force which is bounding the neutron star. Now, regarding this fraction of the gravitational energy to the total mass, so the question is, here we are getting this ratio of 18%. So, is there any limit? Can we obtain any other limit in a similar fashion? Some upper limit or so? Well, you will see that when I solve the TOV equation later on, which is basically the relativistic hydrostatic equilibrium equation or the TOV equation, when I will solve this later on for a uniform density star, then what we will obtain after this solution, it's little bit mathematical, what we will get is this result, and the result is that, let me write it down. So basically the result will be the gravitational energy relative to the total mass. If we do this, the result will be 3 by 5 m by r, right? Here it is m square divided by 1 by m, and this is approximately so 3 by 5 m by r, and you will see from this case what we will get is that this is less than 4 by 15 or 27%. So this is an important estimate, right? So this you will see, we will get. So this is what I wanted to share with you. So basically we are getting sort of absolute limit, right? An upper limit. So an upper limit on the gravitational energy relative to mass.